Welcome to the last lesson of Module 4, where we are going to be talking about distance protection. So, your distance protection is used on HV lines and is really one of your most critical part of your network when you're talking about our HV lines, because if we lose supply to your HV line system, then your entire security of supply is compromised. So, as we already picked up that overcurrent relays cannot provide fast coordinated protection on your transmission systems because they are a mesh system, which means that they are an interconnected system with multiple points of where your supply is going to and where your loads are going to. And then when we looked at our line current differential relays, that was in lesson number 2, these can meet some of the requirements that we require on our transmission networks, but they also require complex and expensive communication links for it to work properly. So then the distance protection was then formed, and this is no longer a unit protection system because it is looking at a wider range of sections, whereas your unit protection just look at a section, but it provides a considerable economic and technical advantage. And unlike your phase and neutral overcurrent protection, the advantage of distance protection is that the fault coverage of your protected circuit is independent of your source impedance variations. So uniquely, your distance relay measures the apparent impedance derived locally from what is measured as your current and your voltage. So they measure the current, the voltage at that point, and then only transform that into your impedance. And if it is within the impedance that is required, then it will not trip, or it will trip according to how we have set it up. So when we talk about the impedance of our transmission line, we usually talk about an impedance that is spread out throughout the length of that line. So if you have a 150-kilometer line from where your first substation is, the impedance will be spread out through that line. So at different points of that line, for example, at 50 Ks, will have a different impedance than what you have at 100 Ks and what you have finally at 150 kilometers. So for this reason, the distance relay can discriminate with relatively good accuracy between what a fault is that is internal to your line and a fault that is external to your line. So it just looks at what is internal to my lines and what is external to my lines. And if it's external, it will not provide protection. If it's internal, it provides your protection. So it measures your apparent impedance during a fault, thereby providing a zone of protection. Okay, so but in this type, we are looking at a different type of zone of protection than what we did previously, and that will be explained in the next slides coming up. This can simply be applied, and it is fast in operation for faults located along most of your protected circuit. It also provides your primary as well as a remote or backup functions in one single scheme, and can easily be adapted to create a unit protection scheme if you apply a signal channel in it. So here is an example where we are showing why the overcurrent system will not work for your distance protection. If you look on the left hand side, you will see that you've got the two transformers going into and feeding a line, and they have a fault that they've named F1. So for you to calculate what that fault current is at F1, they take the impedances of your two transformers and they parallel them, so it becomes a 5, and then you add the 4 of your line to get that 9, and therefore looking at what you have as your voltage, you will end up with a fault current of 7380 amps. Then if you look on your right hand side, they've now removed the second transformer. You've only got one transformer, and your fault is now between the two bus bars where it was at the end in the previous one. And when they calculate here the fault current, they find that it is 6640. So when you have to set your relay in this case, you'll have to say that the relay current setting needs to be within the 6640 amps, but it also needs to be greater than the 7380 amps. So it becomes impractical for you to be able to utilize your overcurrent system for this case. So in the situation like this, it's when you'd either utilize your unit protection, where you look at the transformers as a unit and you look at that line as a unit as well. Or you can utilize the distance protection, which is what we're about to discuss further into this lesson. So looking at our left hand side on top, where you have the impedance relay with directional restraint labeled, you will see that our transmission lines in this case are going to be proportional in length for your distance and your impedance. So what happens under your zone 1, we're talking about a specific line length, and under zone 2, it's another specific line length that you can add on, and then your last one being your zone 3, which is also at a specified line length. And we call these predetermined impedances, in our case, what is called a reach point. So a reach point is a point that your relays will be able to reach for protection of that particular system. Then if you look at the one at the bottom on the left-hand side, what that is written modified impedance relay or MHO relay, and you can see there that we have kind of narrowed it up. Whereas in the first one, it was wide, your circle of radius was wider for your zone 1, zone 2, zone 3. But when you look at the modified impedance now, they are predetermined or their reach point is specific, but you can see that we have made the circles to be smaller so that these relays can really concentrate once they get to our zones, that it does not become too much all over the points. Then looking at my right hand side, you can see here that I've got a network with two generators in it. And in this network, if I had to say that my relay was at where my B12 or at where my bus bar 1 is going to be, then this relay would have its zone 1 at the point that you can see there marked, which is about 80% of that first line. It would have its zone 2 at what I call 120% of that initial line. So it's that impedance or distance. And then the zone 3 is what you would have as the rest of the system. Now I'm going to define the zones much properly for you in what is happening in the next slide. But what I need you to do is to go onto the module that I actually sent you. And if you can't find it on your emails, go to Wise Up and you will see there under your content, okay, your lecture content, your module 4, you will have the actual note there so that you can have this picture as I discuss it going further down. So now we are going to be looking at how the zone 1, 2s, and 3s are formed and how they work. Under your zone 1 protection, which we said was an 80% reach, it means that it can protect that line 1 to 2 up to 80% of it. And if a fault was to occur up to that point where the reach point is 80% of that line, then we want this protection to take out that line immediately. Okay. Whereas if you look now at your zone 2, which we said was set at 120% reach, and it extended beyond your bus bar 2. So it has a typical then time delay for your zone 2, which would be about 200 to 300 milliseconds. And what it means is that your zone 2 would provide a backup protection for faults that are occurring in your line 1, 2, as well as remote or backup for faults occurring on your line 2, 3 or 2, 4 in zone 2. Okay. Then if a fault was to occur on line 2 to 3, your B23 relay needed to trip, not the relay that is a B12, because your B12 is sitting at zone 1. So the impedance seen by B12 for faults near bus bar 2, either on line 1, 2 or on line 2, 3, is essentially the same. Hence, it's not set at your 100%, but we set it at 80% for zone 1. So this makes sure that we avoid any instantaneous operation of your B12 relay or circuit breaker for a fault that is happening only on a line closest to bus bar 2. So in the event that your fault is, let's say, at 110% of that impedance, then you want your zone 2 to be the one that picks up that fault. But because it's within the zone 2 reach, it must be able to trip that fault instantly at that point. Whereas if zone 2 had to do a backup for zone 1, then it would only be able to trip in within 200 to 300 milliseconds. So if I repeat again, your zone 1 reach would be the 80% and it would be instantly. Your zone 2 is 120% and your typical time delay for it is 200 to 300 milliseconds. What is the 200 to 300 milliseconds for? The 200 to 300 milliseconds is for it to still act on your zone 1 protection zone. If your zone 1 failed to pick for whatever reason, then your zone 2 must take out that line, but it needs to have that delay of 200 to 300 milliseconds. However, if you had to have a fault not now on line 1 to 2 reach, but you had to have a fault that was at 120% reach, let's say it was at 110, then this is particularly at zone 2, and you don't want your zone 2 to wait until 200 to 300 milliseconds before it trips that fault. It needs to trip it immediately if it's happening with its own zone that is not covered by your zone 1 point. Am I making a sense? So as long as it's between 80 and 120 reach, your zone 2 must trip instantly. But if it was within that 80% reach, your zone 2 would only trip after the 200 to 300 milliseconds. Then you have your zone 3. Okay, so for your zone 3, how we've defined it in our earlier course where I do protection 3 with the diploma guys, I've made standardized that your zone 3 is now 150% reach. But as you can see in the network that we just had now, it's a complicated network. It's not straight lines from point A up until point E. So therefore here we say that for your zone 3 to be effective, we want to set it at 100% reach of your first point of your line, and then it must be plus 120% reach on your largest or longest line. It can either be your 2 or 3 or 2 and 4, depending on what is the length or the impedances of those lines, you will take the bigger one of those two and set it at that 120% reach of it. Then the table that has just popped up is really a summary of what your zone 1, your zone 2, and your zone 3 does. It summarizes their reach points, the 80% for 1, the 120 for 2, and then the 100% of line 1 plus the 120% of your longest line for zone 3. Then your times of operation. If and these times of operations are looking really at if the fault had to happen in your zone 1 region. So we say the time of operation would be instantly for your zone 1 because it's happening within this region. It would be about 250 milliseconds, which is halfway between the 200 to 300 if it was on zone 2, and about 800 if it was on zone 3. If you had communication link on your line, either using a pilot or you are using your digital or any other type of communication between all your different substations, then we say still your zone 1 will still be instant. However, your zone 2 will now only be one revolution, which is amounting to 60 milliseconds, and your zone 3 would be two revolutions, which is amounting to 120 milliseconds. So the basic principle, if I summarize this slide, for your distance protection really is going to involve you utilizing your voltage that you have for your system, which you need to then divide by your measured current of your system. And that is what will give you your impedance, which will then talk to our apparent reach point impedance. If your measured impedance becomes less than your reach point impedance, it means that your fault will be existing within your line between the relay and your reach point. So it could be up until zone 3, which means that it is covered under your protection scheme. However, if your measured impedance is more than your reach point impedance, okay, and your reach point impedance, I think as you can see from here, your largest would be your zone 3. If your measured becomes more than that, then it means your fault exists outside your line between the relay and your reach point, and therefore that will not be picked up. If a fault occurs in your system, this protection will not pick it up because it's outside even your zone 3 reach point. So to summarize what we have done, we are now going to come and do an example. So here's a network that you are now familiar with because we saw it in our first lesson where we were talking about the zones of protection. So this time around, now we're going to utilize the same network where we want to do our distance protection in. So your line 1, 2, your line 2, 3, and your line 2, 4 all have got impedances that have been given. For 1, 2 is the 6 plus J60, for 2, 3 is the 4 plus J40, and for 2, 4 is the 5 plus J50. So therefore, they want us to first determine our settings, which is your zone 1, zone 2, zone 3. I want you to note that here they've said ZT1, ZT2, ZT3. Sometimes they name them ZR1, ZR2, ZR3. Irregardless of how it's named, it's your three zones, zone 1, zone 2, and zone 3. So they want you to now determine those settings if that relay is the one that is sitting at B12. Then they want us to know or to tell them how long will each of those relays, your Z1, Z2, Z3, take to trip if the scheme is without communication if you have a fault at 20% of that first line. Okay, so that 20% of that first line, obviously it must ring a bell for you that is within zone 1. So at zone 1, how long would it take for you to trip all of them, your zone 1, your zone 2, and your zone 3, if you had no communication and if you had the communication in the scheme? Then your third question is saying that if we have a maximum current on line 1, 2 under emergency loading conditions, that is 1400 amps. Now, we all know that in electrical systems, we have emergency situations whereby you end up loading your system more than you would because you've either lost one of your generating lines or something else has happened in your system. So you load that to be higher than it is usually run at. So in this case, they're asking if we had to have that emergency scenario, of which then that line carries that 1400 amps at the power factor of 0.9. They want us to verify, will the relay trip during emergency loading conditions or not? And you must remember here that last part of the previous slide where we said our measured impedance, if it's less than your reach point, then it means that is within your zone of protection. So your protection will trip. But if your measured is more than your reach point, it means it's outside your protection zone, so therefore it will not trip. So when you answer this question, you must know what is your reach point, and then you must calculate this one, which is your measured, the 1400 amps, to determine if it will trip or not. Then for your last two questions, they go back to that fault P1 and P2 that we had seen also previously. They're still at the same places. And they're asking now that for fault P1 or a fault at P2, which zone relay will trip first between your zone 1, zone 2, and zone 3. So you need to determine where are those. Are they at zone 1, which is 80% of the initial line? Are they at zone 2, which is 120% of it? Or are they at zone 3, which is the 100% of the initial line plus 120% of what you would have as your longest line on your other two? Then once you have determined that, then you can say which one would trip first. Then we go and we have the last question, and it says name the relays as per the naming on the diagram that will isolate the fault P1 from the system instantly, ensuring that your fault currents do not leak in the system. So this one almost goes back to our zones of protection, where you look now at P1 and you say what breakers are there, and there is the B24 and the B42. So those should be able to take out that instantly. And what zone would that be in? It's obviously not zone 1, and it doesn't look like it would be a zone 2. So that probably would be a zone 3 scenario. So let's go to the next slide and be able to work out how to answer all 5 of these questions. So the first thing that you do is you take your VT and your CT ratings that you are given, so that you can work out your reach that you are going to be working with. So having taken those two into account, you end up with a Z multiplied by 1 over 15. The Z being obviously that V over I scenario that you will get. So if we look at now for zone 1 relay, which is 80% reach of the first line, we can say that my ZT1 is going to be 0.8, which stands for 80%. I multiply into the impedance of that first line, which were given as 6 plus J60. Then I can divide by the 15, and I will have what my zone 1 scheme is going to be set at. Then I go to my zone 2. In my zone 2, we remember it was 120% of that line 1, 2. So I do the 1.2 for 120%. I still multiply by that impedance of that line, and then I divide by the 15, and I get my zone 2 reach. Then I calculate my zone 3 reach. And my zone 3 reach is 100% of that initial line, which was line 1, 2, and 120% of your longest line. Now you had a 4 plus J40 and a 5 plus J50 on your other two lines. So the 5 plus J50 will be your larger impedance, meaning it's your longest line. Therefore, you put this, the 100% of the first one and the 120% of the second one, and you get that this is your zone 3 reach. So this is how you will set for this system that we have. Then you go to number B, where they asked if that fault occurred at 20% of your line 1, 2. How would all of the zone 1, 2, and 3 break, or that fault, how long would they take with and without communication? So for zone 1, we know it would be instantly because it's within its reach. For zone 2 to take out that fault, it would wait and act as a backup. So initially it would, if it had communication, it would be 60 milliseconds, which is one revolution. Without communication, it would be there 250 milliseconds. The newest relays are now set at the 200. Okay, that's why I've got 200 in here. But if you gave me the 250, I will still take your answer. Then you've got your zone 3 with communication, 2 revolutions, which is 120 milliseconds, and it is at 400 milliseconds as per the newest relays, but the older versions, which are still used a lot of places, it would be the 500 milliseconds that it would take there. Then we go to our number C, and our number C was now asking if we had to load our line 1, 2 under emergency conditions to be sitting with 1400 amps, what would happen? Would it trip out the circuit or not? So we first go and then calculate that measured impedance. That's what we call it, is the measured impedance that we need to calculate. Yeah. And how do I do that? Well, firstly, I know that my system is sitting at 500 kV, and then I've been given that the amperages are going to be the 1400 amps. So I do the V over I. Then I must not forget, Uguti, I must also divide by the square root of 3 to move into a single phase scenario like we always do for your current scenarios. So then I then end up with an impedance of 13.7, as you can see. Now, for me to know, where does the 13.7 lie? Is it within or outside my reach? I go and I compare it to my zone 3, which was the largest of my settings. And if I take that 0.8 plus J8 I got and I put into a complex scenario, I can see that it is at 8.04. So what does this mean? It means the 13.7 exceeds the 8.04, which means that if that is measured and it's more than my zone reach setting, then my circuit will not trip when that current is into the system, because it is outside my trip region, which means therefore that we can be able to load that line 1, 2 during emergencies up until that 1400 amps. If your emergency tripping scenario gave you an impedance that was less than the zone 3 reach, which is the 8.04, let's say you ended up with 7.95, okay, impedance or ohms, then unfortunately it would mean for you that in an emergency scenario, your zone 3 would be able to take out your line. So you would not be able to have an emergency situation of more than 500 milliseconds, which is really a half a second, if you were looking at not having a communication link in your lines, and only 120 milliseconds with a communication link. Then you go to line point D, that was asking which of those zones, 1, 2, or 3, would take out your P1 and your P2, and we find it would be your zone 3 reach. And then I already answered E, the ones that will take out your P1, and it is your B42 and your B24. And that is all, ladies and gentlemen, for module 4. This is the end of it. I hope this was educational and that you learned something from it. And should you be given an example that you can be able to work it out utilizing what you have learned from this module as a whole. Thank you. We now have 2 more modules left until we have reached the end of the course.